class we are going to see about the measurement of high voltage. First let us see about the constraints in measurement of high voltage, then two basic methods used for measuring high DC voltages, and then advantages and limitation of these methods. So we are going to see about this in this video. First let us see what are the constraints in high voltage measurements. First one is safety. Second one is linear extrapolation, then electromagnetic interferences, then atmospheric factors. So these are the constraints in high voltage measurements. In industrial testing and research boundaries, it is essential to measure the voltage and currents accurately, ensuring perfect safety to the personnel and equipment. So that we have to go for the safety. First preference is go for the safety. So measuring devices and personnel must be protected against over voltages and any induced voltages due to stray inductance and capacitance. It is the first factor. So measuring devices and personnel must be protected against over voltages and any induced voltages due to stray inductance and capacitance. So it is the first factor regarding high voltage measurement. Therefore, a person handling the equipment as well as the metering devices must be protected against over voltages and also against any induced voltages due to stray coupling. That is called as stray inductance and stray capacitance. Then one is linear extrapolation. Linear extrapolation beyond the range is not valid. Hence, they have to be calibrated for the complete operating range. Linear extrapolation beyond the range is not valid. Hence, they have to calibrated for the complete operating range. So, it is the second factor, that is the second constraint for high voltage measurement. Next one is electromagnetic interference. We will see the electromagnetic interference. The electromagnetic interferences causes error in measurements of impulse voltages and currents. Hence, these must be minimized. Electromagnetic interference causes error in measurements. With communication lines, they have electromagnetic interference. So, in order to avoid the electromagnetic interference, we will go for the high voltage measurements. So, high electromagnetic interference causes error in measurements of impulse voltages and currents. Hence, these must be minimized. And the next factor is atmospheric factors. That is, measurements are affected by atmospheric conditions. Hence, air density correction factor along with humidity must be introduced. Measurements are affected by atmospheric conditions. So, due to weather conditions, it may be affected. Hence, air density correction factor along with humidity factor must be introduced for the high voltage measurement. So, the first one is safety, second one is linear extrapolation, then electromagnetic interference, then atmospheric factors. They are the constraints in high voltage measurements. So, let us see the methods used for the high voltage direct current. So, method 1 is high ohmic resistance with microammeter. That is the first method. High DC voltages are usually measured by connecting a very high resistance, that is a few hundreds of mega ohms, in series with a microammeter as shown in figure. Only the current I flowing through the large calibrated resistance R is measured by moving coil microammeter. The voltage of the source is given by the Ohm's law, that is V equal to IR. So, voltage drop in the meter is negligible. As the impedance of the meter is only few ohms compared to few hundred mega ohms of the series resistance R. A protective device like a paper gap or a neon glow tube or a Gina diode with a suitable series resistance is connected across the meter. See the diagram. A protective device like a paper gap, a neon glow tube or a Gina diode with suitable series resistance is connected across the meter as a protection against high voltage in case the series resistance R fails or flashes over. So it is a protection device. It gives protection against high voltages in case the series resistance R fails or flashes over. This is the protection device. So it is used to protect the device, that is the equipment, from the over voltage. So it is like a paper gap or a neon glow tube or a Zener diode. The ohmic value of the series resistance R is chosen such that current of 1 to 10 microamperes is allowed for full scale deflection. The resistance is constructed from a large number of wire wound resistors in series. The voltage drop in each resistor element is chosen to avoid surface flashovers and discharges. Let us see the circuit operation. High DC voltages are measured by connecting a very high resistance, that is by several hundred mega ohm, in series with the microammeter. The microammeter is selected such that current of 1 to 10 microampere flows for full scale deflection. The microammeter is selected such that the current of 1 to 10 microampere flows for full scale deflection. Then the current I flowing through the large calibrated resistance R is measured by the moving coil micrometer. Why we are using moving coil micrometer? For DC measurements, we are going for the moving coil meters. The voltage drop in the meter is negligible compared to that across the resistance R. Since the value of resistance R is very high, the voltage drop in the meter is negligible. A protective device like a paper gap, a neon glow tube, or a Zener diode with suitable series resistance is connected across the meter to protect against high voltages in case series resistance R fails or flashes over. It is the circuit operation of the series resistance micrometer. Let's see the application for this method. It is used for measuring DC voltages up to 500 kilovolt with an accuracy of plus or minus 0.2% is the application of series ammeter method. The advantages is the circuit is simple and low cost, but it has drawbacks. We will see the drawbacks. In order to rectify the drawback, we are going for the next method. The first one is Iomic series resistance micrometer. The limitation of these methods are power is dissipated in the circuit causing source loading. Power is dissipated in the circuit causing source loading. Then measurements are affected by temperature variations. So it depends upon Ohm's law. Ohm's law will be applicable only for the constant temperature, but the measurements are affected by temperature variations in series resistance microammeter method. Therefore, the measurements are affected. Then the circuit is sensitive to mechanical stresses. The circuit is very sensitive to mechanical stresses. It is the third one. And next one is voltage dependence of resistive element. Voltage dependence of resistive element. So these are the factors or the limitations of the series resistance micrometer method. Let us see the resistance potential divider method. It is a second method. So in this method we are eliminating the drawback which is applied in the series resistance micrometer, that is the temperature dependence and voltage variation is eliminated in this method. So figure shows the resistance potential divider. So in which an electrostatic or high impedance voltmeter is employed. The influence of temperature and voltage on the elements is eliminated in the voltage divider arrangement. The high voltage magnitude is given by R1 plus R2 divided by R2, that is the potential divider concept. The voltage across the resistance R2 is R1 plus R2 divided by R2 into V2, where V2 is the DC voltage across the low voltage arm R2. V2 is the DC voltage across the low voltage arm R2. With sudden changes in voltage, such as switching operations, flashover of test objects or source, short circuits, flashover or damage may occur to the divider elements due to the stray capacitance across the elements and due to the ground capacitance. So to avoid these transient voltages, we have a protection device. And to avoid these transient voltages, voltage controlling capacitors are connected across the elements. To avoid the transient voltage, voltage controlling capacitors are connected across the elements. A corona-free termination is also necessary to avoid unnecessary discharge at high voltage ends. Therefore, a series resistor with a parallel capacitor connection for linearization of transient potential distribution is there. The potential dividers are made up of 0.05% accuracy up to 100 volt and with 0.1% accuracy up to 300 volt and better than 0.5% accuracy for 500 kilovolt. Let us see the circuit operation. A resistance potential divider with an electrostatic or high impedance voltmeter may be used for measuring high DC voltages. The influence of temperature and voltage on the element is eliminated in the voltage divider arrangement. The influence of temperature and voltage on the elements is eliminated in the voltage divider arrangement. Then the magnitude of high voltage is expressed as V equal to R1 plus R2 divided by R2 into V2. That is across the resistance R2, the magnitude of high voltage is expressed as V is equal to R1 plus R2 divided by R2 into V2, where V2 is the voltage across RL. A corona-free termination is necessary to prevent discharges at high voltage ends. So, corona, when it will occur, above 30 kilovolt, the corona will occur. So, the corona-free termination is necessary to prevent discharges at high voltage ends. So, for that we are using a capacitor. With sudden change in voltage or short circuits, flashover or damage may occur to the divider elements due to stray capacitance. So, voltage controlling capacitors can be connected across the divider elements. Let us see the application. It is used for measuring DC voltage up to 500 volt with an accuracy of plus or minus 0.5%. Regarding series ohm micrometer, the accuracy is plus or minus 0.2%, but regarding potential divider it is 0.5%. Let us go for the summary of this class. The measurement of high voltages need careful considerations to safety, electromagnetic interferences, interpolation and atmospheric factors. High resistance in series with microammeter method involves temperature dependence and source loading. So, in order to avoid that, we are going for the potential divider method. So, high resistance in series with microammeter method involves temperature dependence and source loading. And finally, potential divider method overcomes the drawbacks of above method, that is the series microammeter method, in which the method involves temperature dependence and source loading. So, to avoid this, we are going for the potential divider method. In the potential divider method, it overcomes the drawbacks of the series microammeter method, like dependence on temperature and voltage variations. Thank you.